Hi everyone, my name is Adam, and I'm one of the members of the Flat Moon Society. I'm joined today with Danny, John, Josh, Oran, Rohan, and Ryan. Our proposed mission MoonCubed, involves sending a group of autonomous rovers to the moon to search for water in 2 lunar craters. The mission objectives for Mission MoonCubed were set by the AIAA Student Design Competition specifically for the Robotic Lunar Crater Resource Prospecting Mission. Listed within the AIAA design requirements and constraints, the primary objective of the mission is to determine the locations and quantities of water in 2 lunar craters. In terms of secondary objectives, the AIAA requirements requested that the scientific data returned is maximized. To meet these requests, the Mission MoonCube team has decided to use the scientific instruments on board the MoonCubes to prospect for other useful resources on the moon while also searching for water. Additionally, the team has proposed future plans for the mothership after the primary mission comes to an end. These plans include lunar mapping or serving as a communication satellite for other lunar missions. In order to ensure that the mission objectives are met within the cost, design, and schedule constraints as listed by the AIAA Student Design Competition, requirements and constraints for all aspects of the mission have been carefully selected by the Mission MoonCubed engineers. These constraints and requirements are divided into 3 sections: functional requirements, operational requirements, and constraints. The functional requirements for the mission define how well the system must perform to meet the objectives. Some of these requirements include detecting water up to a depth of 10 meters and covering 600 square kilometers of the surface per crater. The operational requirements for the mission determine how well the system operates. Some of these requirements include MoonCube battery life of 72 hours and survivability on the lunar surface. The constraints for the mission define and limit the cost, schedule, and implementation techniques available for reaching the objectives. Some of these constraints include a cost of $500 million in fiscal year 17 and a mission completion date by December 2024. Mission MoonCube will consist of the following 3 primary phases: transport, deployment, and operation. Phase 1, the transport phase, includes the launch from Cape Canaveral and orbital trajectories and maneuvers from low Earth orbit to translunar injection orbit, followed by insertion into lunar orbit. Phase 2, the deployment phase, involves the deployment of the lunar buses and MoonCubes. Phase 3, the operational phase, will begin once the MoonCubes have been deployed in the Shackleton and Cabeus craters and will last until the end of their operational periods.
Hello, my name is Danny Savoy and I'll be going over the structures and mechanics section as well as ground control. Shown here is the full payload before the lunar bus is detached from the craft. Each craft was modeled in detail to get accurate natural frequency and moment of inertia calculations, as well as thermal simulations. The mothership maintains an orbit during the mission. The use of aluminum for the frame and the arms connecting the antenna to the craft. Aluminum was chosen due to its high cost-to-mass ratio. The total volume of the mothership is 30.59 cubic meters, which is 72% of the total volume of the payload. The 2 arrays facing Earth are 1 meter in diameter and communicate with the near-Earth network, while the 2 facing the Moon communicate with the lunar buses. The rocket engine and the odd-2 control nozzles allow the mothership to navigate and adjust during the mission and secondary missions in the future. 6 lunar buses will detach from the mothership and descend to the lunar surface, 3 in each crater. They will make adjustments as they approach the landing zone while carrying a payload of 1,000 kilograms. So the frame will undergo various stresses and vibrations as the adjustments are made. The side-mounted GPR extends 0.6 meters outward so they can read the terrain beneath the craft. Each craft has a volume of 2.18 cubic meters while in storage, and then each craft fits together into the nozzles. Each craft fits together as the nozzle slides in the hole on top and below the craft. The 4 legs extend outward during the landing and are made of carbon composite AS4 due to its ability to embrace from shock of the impact. The bottom drops out so the MoonCubes can deploy in all directions and there's no single point of failure.
The last craft is the MoonCube. 50 MoonCubes are in each transport, with a total of 300 distributed onto the Moon's surface. The frame is made of aluminum, much like the structures on all the other crafts, but these frames are much thinner since there are so many rovers and they do not have to undergo as much stress. The wheels are similar to the Curiosity rover, using a similar suspension system. They maintain folded within the MoonCube until deployment to take up as little space as possible. The wheels are aluminum with titanium spokes for stability. The titanium can withstand the stress of rolling over the rocky environment on the Moon. The first sensor is the GPR, which is 0.25 meters by 0.25 meters to ensure it can receive data from 10 meters down and fulfill the performance mission requirement. The other 3 sensors are used to dig up and analyze the regolith. All sensors are contained within the 12U MoonCube.
Hello, My name is Joshua Elcricken, and I was in charge of updating the launch vehicle to represent the new recurrence of mission MoonCubed. Previously, the mission called for a singular Falcon 9 launch vehicle. However, due to an increase in the payload mass, an upgrade to the Falcon Heavy architecture was required to provide the necessary Delta V to establish the proper parking orbit. The Falcon Heavy will satisfy the launch requirements by providing 64 metric tons to LEO, while having significantly lower costs than the alternatives at only $90 million per launch.
The mothership will function as the upper stage of the mission for transporting the payload from low Earth orbit to low lunar orbit using an Aerojet AJ-10-190, which was also used on the Space Shuttle Orbital Maneuvering System. It is equipped with 16 ACS thrusters for orbital maintenance and attitude control. Both systems will use monomethylhydrazine and mixed oxides of nitrogen propellant to reduce complexity and overall mass. The lunar bus propulsion system will function similarly to the lunar descent stage of the Apollo missions. It will implement an AJ-10-190 engine for descent control and 8 ACS thrusters for attitude control. Once again, monomethylhydrazine and mixed oxides of nitrogen will be the propellant used for both systems.
The ground control software is the main computer of the entire mission. It integrates sensors with hardware and programs the embedded system on each craft. Most maneuvers will be automated, but any emergency procedures will be programmed by ground control. The GCS communicates with the mothership using the near-Earth network. The ground control station was used Jet Propulsion Labs location due to its experience with similar robotic missions like the Lunar Flashlight. The three most important requirements to the GCS is to be able to communicate and monitor in real time, as well as store important information sent back from the mothership. The ground control station will be used regularly during testing as the aspects of each three crafts. All teams are involved with every step of the process.
Hi, my name is Ron Rosenberg, and I'll be talking about the communication system for Project MoonCubed. The UHF comm band was selected for its low power consumption and lack of atmospheric attenuation on the moon. Each MoonCube is equipped with a single MER-derived low-gain antenna, which allows it to communicate with its lunar bus at 256 kilobits per second. Each lunar bus has 4 of these, which allows it to communicate to its MoonCubes at 1.8 megabits per second and 230 kilobits per second to orbit. Also equipped with the DHONs, which allows us to communicate 578 kilobits per second to orbit. Each mothership has 2 high-gain parabolic antennae, which allows us to communicate 256 kilobits per second to its assigned lunar buses. The S-band communication system was selected for Earth-Moon communications due to its availability on the near-Earth network. This allows us to communicate from NEN to the mothership at 256 kilobits per second. The mothership is equipped with 2 parabolic high-gain antennae that allow to communicate with NEN at 3.5 megabits per second. An omnidirectional antenna is available for use during tumbling and maneuvers, and this provides a link to transmit scientific data to Earth, which explains why the mothership has such a high data rate compared to NEN.
Hello, my name is Joshua Elcricken, and I was in charge of developing the CDNH architecture for mission MoonCubed. The first main design goal was to create a robust CDNH system for the mothership. It acts as the final link between the rovers on the lunar surface and ground control. With this in mind, the computer and OS were chosen primarily for reliability and heritage. The BAE RAD 5545 was chosen as the computer for the mothership. This architecture is an updated version of the BAE RAD 750 architecture. This architecture has been used on many missions such as Curiosity and Kepler and maintains radiation hardening. Wind River's VX-Works was chosen due to its prevalence within the industry, support for Wind River, and heritage with missions like Curiosity. The lunar and bus CDNH architecture has the benefit of redundancy by the nature of the mission. As a result, while each lander is still important, a singular failure will not be catastrophic. With this in mind, in order to minimize the cost for both hardware and software, CubeSat technology was used to create the architecture. The 2 EnduroSat CubeSat computers were used in parallel to provide redundancy. CubeOS was chosen as the operating system in order to minimize the custom software needed to be written and not having any licensing fees associated with it. The MoonCubes will have a very similar CD&H systems as lunar buses, with only one EnduroSat computer.
Aspects of guidance navigation control for the mothership include navigation through translunar injection, as well as orbital and attitude determination. This will be done by the instruments of 2 Astro APS star trackers, 1 Moog core sun sensor, and 2 Honeywell HG1700 IMUs. The aspects for guidance navigation control of the lunar bus involve altitude and attitude determination throughout the descent maneuver from the mothership to the lunar surface. This will be accomplished by 1 laser altimeter, 2 Astro APS star trackers, and 2 Honeywell HG1700 IMUs.
Hi, this is Rohan, and I'm going to talk about the power subsystem. The mothership will be powered by 2 solar arrays supported by secondary batteries. Solar arrays are a reliable and cost-effective means of power to any sun-exposed satellite. And the secondary batteries provide backup power in the instance of no direct sunlight. Solar arrays have a very long lifespan that will allow the mothership to be repurposed for a future mission. The lunar buses will be powered by hydrogen peroxide fuel cells. These fuel cells provide high power per unit mass, which will allow the lunar buses to run thermal systems in transit to the lunar surface and also minimize MoonCube power consumption until deployment. The fuel cells will also provide sufficient energy to run constant communications over their 7-day lifetime requirement with less than 8 kilograms of fuel per lunar bus. The MoonCubes will also be powered by hydrogen peroxide-based fuel cells. Because of the functional requirements, MoonCubes are required to operate for a minimum of 72 hours at a total power consumption of 6,120 watts. So only 5 kilograms of fuel is required. With fuel cells, mission operational life can be drastically increased without adding significant mass. The fuel cells are 55% energy efficient and will have to be manufactured in large quantities.
Ryan Bish, Thermal Control Subsystem. The mothership will be equipped with heat pipes, louvers, and thermal control coating. The heat pipes will distribute thermal energy from the surfaces and components to maintain equilibrium, while the thermal control coating, which resists ultraviolet and infrared spectrum intake, ensures that the louvers are the primary means of adding heat to the system. The lunar buses will be equipped with heat pipes, louvers, and electric heaters. The heat pipes will distribute waste heat from the fuel cells by means of conduction, the louvers will either dump excess heat or resist outward heat flow, and the electric heaters serve the primary function of ensuring that the fuel cells are able to wind up to operating temperature and will also add thermal energy to the system if necessary. Like the lunar buses, the MoonCubes will be equipped with heat pipes and electric heaters to perform the same duty as they do aboard the lunar buses. MoonCubes will also be internally packed with multi-layer insulation, a radiation transfer barrier composed of backed Teflon inner layers and aluminized mylar outer layers that will serve as a means to preserve thermal energy in an environment where temperatures range as low as negative 238 degrees Celsius.
Hi, my name is Ern Rosenberg, and I'll be talking about the payload system. The side-mounted ground-penetrating radar, or SMR, is derived from the Mars 2020's RIMFAX GPR, ground-penetrating radar. It's a medium resolution for low-altitude mapping of water and mineral deposits, and it's used to optimize landing selection. Each lunar bus is also a part of the Lunar Exploration Network, which allows lunar bus to lunar bus to MoonCube communication. This fulfills the functional requirement through accurate transportation of MoonCubes and coordination. MoonCubes are autonomous rovers operating with swarm robotics, and they are equipped with 2 different sensors. The first one is RIMFAX, which is a ground-penetrating radar that allows high-resolution mapping of water and mineral deposits at depths greater than 10 meters. It has low power consumption compared to previous GPRs. The lunar camera, laser spectrometer, and drill are liquid. It's adapted from Curiosity's ChemCam and is used to identify water and mineral deposits on or near the lunar surface, compared to RIMFAX, which is used to look at depths greater than that.
The primary objective of mission MoonCubed is to determine the quantity and location of water in 2 lunar craters. After a year's worth of design conception and research, the Flat Moon Society has formulated a redundant plan using 1 mothership orderer, 6 lunar bus landers, and 300 MoonCube rovers that will be capable of completing the primary objective within the requirements set forth by the AIAA design competition. Thank you for listening.